So we left off with the advantages of this parallel thing. Um, Actually, let's back it up a little. Yeah, we're probably somewhere in there. So the advantages of the parallel circuit: more than one thing can be plugged in at the same time, does not dim. If one light bulb goes out, they all stay on. Current doesn't stay the same for the entire circuit, but I don't think that's really an issue, that current doesn't stay the same. But it does use more energy the more stuff you have on. So more current means greater flow. Could be hotter wire burn the house, but that doesn't usually happen because the houses are pretty well made with those protections. Alrighty, so which is better, the series or the parallel? Well, most things are in your house are wired in parallel, so you can use more things at one time without decreasing the amount of current flow that you have available. So, so the point is, the more stuff you plug in, it doesn't decrease or increase the intensity. It stays the same. You can have all kinds of things on if you don't have too many things plugged into one circuit. Okay, so there is that increased risk of fire the more stuff you plug in, but that's why you have fuses and circuit breakers that are wired in a series in your house. So it's that fuse burns through, where the circuit breaker flips. It's in a series. It turns everything off on that circuit. Okay, so toll booth explanation of how this parallel stuff works. Guys, if you had 13 toll booths on the interstate highway, but they're all in a series in a line, that doesn't help get all the traffic through there because you got all these toll booths in the way. But if you put those toll booths in parallel, so you got a toll booth, toll booth, toll booth, all in parallel, so cars can choose which path to take, everything goes much faster. The flow is so much more easily done if you have everything in parallel, because there's less resistance to that flow and the traffic is greater. If you have all the toll booths in a series, not only are you slowing down things behind the toll booths, but you're slowing down things on the other side because not many cars can get through. So the advantages of the parallel setup is less resistance, okay? Easier for stuff to flow. So here we go, guys. There's your schematic down there. So the resistors are side by side in that the positive side is on both of these. If one of these burns out, you still have the same flow through the other one because you still have the same resistance to that you had before. So you're going to have the same flow, and we don't have to have both of those things on. But the more paths you have, the less resistance. Because remember, guys, these light bulbs that you guys already used, they're little tiny pieces of wire. If you have two little tiny pieces of wire but stuck together, you're doubling the area of that thing. You're making it twice as thick. Twice as thick means twice as easy to go through, or half the resistance. So by having things in parallel, you actually decrease the resistance, and that's why we use this funky formula right over here to find the total resistance. It's 1 over the total resistance is 1 over the R, 1 over the R2, 1 over the R3, or 1 over the R4 if you have that many. But in this situation, we'll see the resistance actually decreases the more things you have plugged in. Finally, have so many things plugged in, it's like you have nothing plugged in at all. I mean, there's very little resistance with so many paths. So, por ejemplo, if both of these resistors are 4 ohms, it's like having one 2 ohm resistor, because you're making it twice as easy to flow through when you have twice as many paths like that. So since current offers 2 equal paths away, so half the charge goes one way, then the other way, you actually make it twice as easy because you're making the openings for those charges to flow twice as great. Okay, so in other words, you have 4 amps coming out of the battery, 4 amps coming here. Some goes this way, some goes this way. So if they have equal resistances, half will go here, then the other half will go here. Guys, you can't have 2 coming through here and 1 coming through here, because then you lost an amp somewhere. It's the law of conservation of charge. Whatever you have coming in, you have to have coming back out, and 4 amps coming right back to the battery. So you have to have 4 amps going. You're losing energy in terms of the potential. The voltage is dropping as they go across here, but not the flow of current. You can't get rid of it. That's the law of conservation of charge. Okay, so all the paths are used. The current divides up into all those branches. In this case, you're making it 3 times as easy to flow if they're all the same resistance. So that would be 1/3 the resistance. Okay, but if they're different resistances, it's not, the math isn't quite that easy. But the math for the current's not hard at all. Whatever comes in comes back out. So the total current going in is 4. You have to have 4 coming back out. That means it splits into, in this case, a 2 and a 2, or you can split into 3 and a 1, but it has to total 4 amps everywhere. Okay, so now let's look at the potential, which is potential sometimes called as voltage. It's the potential drop, which is what we call the voltage or voltage drop. So anytime you pass through a resistor, you're going to drop in energy. Okay, you're going to drop in voltage or electromotive force as you go across this thing, because you have more energy before it than you do afterwards. You can't get something for nothing. Okay, so the voltage drop across a resistor it chooses to pass through must equal the voltage of the battery. Because guys, you're hooked up to here the positive, positive, straight to the positive, straight to the negative, negative, and negative. They all have to be at the same voltage. Have to be. So they're all going to have the same voltage drop. Now they're going to have different current running through each one depending on the resistance. The higher the resistance, that means the lower the flow of current, but it is the same potential across everything. So the voltage is the same everywhere in a purely parallel system. Alrighty, so here we go. So in parallel, voltage is the same, but current is not. In a series, you only have one path. The current has to be the same. But then to find the resistance in series, the resistance increases with more. It decreases with more resistance in parallel, because you're just adding another path. Guys, if I were to back up for just a second here, if I didn't have this R3 here at all, it doesn't make it any easier to flow through here. So let's say if I take away the R3, then I put it back in. If I put in the R3, it doesn't make it harder to go through the R1 and the R2. It just adds another path. It doesn't make it any harder for these two. In fact, by adding another path, it makes it easier for the whole circuit for more flow to happen. So the resistance drops every time you add a resistor. All right, let's do some math. So we know all the resistances, so put those in the table first. There they are. Let me move my face somewhere else. So the voltage is the same everywhere, but now we can add these things up. Now remember, it's fancy math. It's 1 over the R plus 1 over the 100 plus 1 over the 100, 1 over the 50 rather. So by the time we do all that math, it's down to 25. And you might say, how did that happen? All right, well, let's try to draw a little bit. And I have a drawing utensil right over here. Okay, so if I have a 1, whoops, that's not my drawing utensil. If I do a 1 over 50 plus 1 over 100 plus 1 over 100, remember that equals 1 over the total R resistance. Well, guys, I can't add that until they're all the same common denominator. So I got to multiply this by 2, that by 2, so now they're all 100. So this equals 2 times plus 1, that's 4 100ths. And that is 1 over RT. So now I can flip it. I can't flip it before that. The inverse of this, 1 over RT is 4 over 100, or RT over 1 is 100 over 4, which is the 25 ohms. Okay? So now that we know that's 25 ohms, to find the current, it's the voltage over the resistance. So that's the 12 divided by 25, which is a little less than half an amp, 0.48 amps. So we have 0.48 amps coming out of the battery, but it splits in 3 ways. So where's most of it going to go? R1, R2, or R3? Well, more is going to go to the R1 because it's less resistance. So being less resistance with the same push, more is going to flow through here. And equal flow will go through the R2 and the R3 because this one is not harder to go through than the other. But all you have to do is to find your current is take your voltage divided by the resistance in each case. So you got 0.24 and 0.12, 0.2. You add these up, it's 0.48. So this is the law of conservation of charge. You have 0.48 coming in. Half of that goes this way because these two added together have the same resistance as the R1. You go 1 over 100 plus 1 over 100. Well, the total resistance together is 50 right here. So these two have the same resistance as this one, so half the current goes this way, half the current goes through those both ends over here, but they rejoin for the total current of 0.48 over there. Okay? All right, so we're going to go quickly through a couple different kinds of current. One's direct current. That's the only kind we have to know about for the AP1. Current only goes in one way, like your solar cells, your batteries, which are chemical reactions that happen. Those are all direct current. Current only goes in one way. Alternating current is how our power generation works in the United States of America and most everywhere else. In fact, even our power generation by solar cells or wind turbines, well, it turns out to be AC, it's all converted to AC or alternating current for reasons that it's easier to transport in terms of AC, because the electrons really don't go anywhere. They just go back and forth, back and forth, back and forth. Where direct current, they actually have to travel from one spot, clear back to another spot, and clear back around. So generators do the AC thing. It's a more efficient way of using energy. But direct current is what we use on a lot of our circuits, though, and a lot of your electronics and everything, the different spots. Alrighty, we're at about the end here, guys. So rank the bulbs according to brightness. Well, guys, they're all similar types of bulbs. Okay, so which one's the brightest? Pause and put them down from brightest to dimmest bulbs. Pause and take a few moments. Now that you've unpaused, you should notice that the A is the brightest because 100% of the current goes through the A, right? 100%. Then it divides to this route and the right route, the left and the right. Well, which is it 50-50? Well, that depends. These bulbs are the same, but let's look beyond. Look at these bulbs, guys. How does the resistance of E and F compare to the resistance of the D by itself? E and F are in parallel. That lowers the resistance. That cuts the resistance in half. So that means these two together have half the resistance of this one, so more current goes through the C bulb than the B bulb. So the next brightest bulb is going to be the C, followed by the B. Are we going from brightness? According to brightness, I'm using our model over there. Okay, so all the current goes through A. That has to be the brightest. But what happens on the B and the D is that this path has more resistance than this path. Because the E and the F together, combined together, have smaller resistance than the D. That makes it actually an easier path to go through here. So A is the brightest, C is the next brightest, but because the current splits in half, E and F are actually the least brightest. B and D are the same brightness because you have the same current that goes through the B as the D. There's only one path to go through. So more than half the current goes to the right, less than half on the left. But even though it's less than half, you're not splitting it up. So B and D will be brighter than the E and the F. So the answer is the A is the brightest, followed by the C. The B and the D are the same. Then the E and F are also the same brightness, but they're at the end. And there's your reason. Okay? You can pause it and read it, or I'll just pause for a little bit longer time because I've got a few more minutes that I can use according to the YouTube there. And there's your whole description, which is basically the same thing, probably, that I just said. All right, guys, I'm not getting any younger, so I'm going to go ahead and stop the video. You can keep on, pause it yourself and keep reading, or whatever you want to do there. This is that was the end. That's what I thought. All righty. Have a good one.